Physics. I sent you the link to the book before. The link for the book.
I think you sent it in chat and I downloaded it on my PC, but I'm on my laptop right now.
Let me see if I can find that thing again. It must be in your email. Could you check your email?
I checked my email. I think you sent it on chat, that's why.
Okay.
Okay.
I'll send it again. And Excel International A-level Physics Student Book 2. Here, uh, I need one. Oh, Gmail, 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 Gmail. Coke beer is falling. Your blog. Wow. Control V. Could you send me your email address in the chat? Google Meet chat.
Yes.
Oh, it was oh yes, found it. Found it. Found it. Physics student book 2. Sent. Okay, so what had we done in the last class? In last class, we had a revision of momentum. We talked about elastic and inelastic collisions, that how in elastic collision, the momentum and the kinetic energy, it stays the same. However, in inelastic collision, the kinetic energy changes.
Uh-huh.
Okay. Okay, inelastic collision example. Okay, kinetic energy is not conserved. Then we talked about the relationship between kinetic energy and the momentum. So for example, if we are given a question in which instead of velocity we are given kinetic energy, momentum and mass, so how to interplay with these three quantities to find out the missing one. Okay, this next what we are
Which one? What? Momentum, mass, and
kinetic energy. So
momentum, mass.
we take the definition of kinetic energy.
Okay.
It's right. I haven't started displaying my screen yet. Wait. A window. We didn't revise this thing. Looks like. Okay.
No.
Okay. So now you can see my screen, right?
Yes.
Okay. So if I have got the formula for momentum, it's mass times velocity. And if I find out the value, I mean how I calculate velocity using momentum and mass, the relationship would be velocity is equal to momentum divided by mass. Correct?
Right.
I put this calculation of velocity in the equation of kinetic energy, half mv squared. So it becomes half p squared by m squared.
Okay.
Half m times p squared by m squared. So 1m cancels the square in the denominator, and eventually it becomes kinetic energy is equal to p squared by 2m.
Yeah.
Okay, so I told you that we use this. We solved a few examples where we calculate the we calculated the energy of particular bodies, and by virtue of knowing other known quantities, we said that we could predict different particles. If we find out different, uh, let's say, qualities or different quantities for a particular particle, we can predict what sort of particle that is.
Right.
Okay, so this is what we did in the last class. Now what we want to do, there was then this revision of what is impulse. For impulse we said that impulse we can calculate in a number of ways. So for example, it can be force multiplied by change in time. So if force is being applied for a particular amount of time, that would give us impulse. We also said that impulse could be change in momentum.
Uh-huh.
Okay, and then we compared the two. We said that change in momentum is equal to force multiplied by change in time. So this is what we have done. The next thing that we have to start is momentum in two directions. Again, there is a way in which this thing has been explained in book or methodology which would help you in M2 as well. The same way we did for momentum, we took a slightly different approach from what the way it was explained in the book for unit 1. But this
Uh-huh.
thing, it would the way we learn it, it would help us understand it for
M2.
M2 and other topics that we cover. Okay, so on slide
Okay.
4 of Jamboard, Bismillah. Allow screen to rotate this. Okay, so the thing that we have to remember is that we know that momentum is conserved. So far, we had been dealing it that way. Now, what we have to, if we further expand that statement in a bit, so we say is equal these, I mean, this statement was true when things were happening on just one plane, x plane or y plane. What about when things are colliding at an angle to each other, and then they move off at a separate angle to each other after collision? So what happens then? In that case, we revise this statement a bit, so we say momentum before collision, and then we say along. Okay,
Okay.
similarly, it would be okay. Let's assume that we have got a stationary body lying over here, and let's say that the due to the spin of the first body, this one, this let's call this M1, and let's call this M2. Let me draw M2 in a different color. So we have got M1 and we have got M2. Okay, so after collision, M2 moves in this direction at an angle theta 1 to the horizontal. Here is M2 after collision. Okay, and
Okay.
M1, it moves off in this direction, M1, with an angle theta 2 to the horizontal. Okay,
So
so
both of them are like straight right now, like
initially, let's
beside each other.
I begin with an easy example in which both of them, they were moving. I mean, the second one was stationary, the first one was moving along the x-axis when it came and hit him.
Okay.
Later on, I'll add
Okay.
that complexity as well, so that we know what would happen if it initially has an angle or not. In any case, this is the statement that you have to remember. This is the key statement, and we'll be referring this back to this again and again. Momentum before collision along x-axis, total momentum of all the bodies along x-axis before collision, and total momentum of all the bodies uh, after collision along x-axis. So now that the
Yeah.
same law of conservation that we had previously, we paid no attention to along. We never said along x-axis or y-axis because all the things, they were moving along the same axis. Now, since they're moving in xy plane and they have an angle, I mean angle to the x-axis, we'd be saying along what axis? Okay, we'd be breaking down the velocity. The mass, obviously, being a scalar quantity, it cannot be broken down into components. Velocity being a vector quantity, it would be broken down into its components. Okay.
Right.
Okay,
Okay.
so again, as we have ascribed these bodies masses of m1 and v1, let's say that their initial velocity was u1 and this one had an initial velocity of u2. So now I will have to do things separately. First along the x-axis, so I will apply this law of conservation of momentum. I'll say along x-axis, along x-axis. So what is the mass and momentum of first body along x-axis? m1 u1. What is the momentum of second body along x-axis before collision? m2 u2. Nothing new in it.
Right.
Okay, but now the velocity with which the first body shoots off after collision is v1, and for the second body it is v2. Okay, so along x-axis, what would be the component of this body 1 along x-axis after collision? It would be
Um,
hmm,
V
m1
M1 uh
hmm, hmm,
cosine.
hmm, m1 uh, v1 cos theta 2,
Uh,
cos theta 2, because it's making this angle theta 2 with the x-axis.
right.
Okay, and the momentum, we add to it the momentum for the second body, which would be equal to m2 v2 but cos theta 1, m2 v2 cos theta 1.
Right.
Okay, so I hadn't given angles to the bodies before collision. Now you understand, even if those bodies they had angle, first of all I'll choose a frame of reference. I'm talking with reference to x-axis or with reference to y-axis. We usually choose with reference to x-axis all the angles that we are calculating. Okay, so if these two bodies they were moving at velocities with an angle to x-axis before collision, we would have taken their x components only.
What?
This u1 and u2, right now I am assuming that they're not moving at an angle to the x-axis. First of all, my frame of reference for all this discussion is x-axis. All the angles that I'm talking about, they are with reference to x-axis. In reality, in for example a difficult question, you could be given a question in which your frame of reference is not x-axis, your frame of reference is y-axis. That is first thing.
Okay.
Okay, whatever the case, whatever your frame of reference is, we are always going for the horizontal components when we're talking about along x-axis, right?
Right.
In this particular case, the bodies, since they were moving, they had the u1 and u2 along x-axis only. We didn't have to get into the hassle of breaking them down into their components of vertical and horizontal.
Right.
Okay, had they been moving at an angle, had u1 and u2 had been at an angle with respect to x-axis, we would have taken their x component, which we would have got by m1 u1 cos theta and m2 u2 cos theta,
Like this.
like the second one, like after collision.
Yeah. Okay.
Okay, so for example, I mean, I could give you an example over here right now, but I want to revert back to this situation, because let's say this u1 was in this direction for m1. Then instead of taking m1 u1 over here, we would have taken let's call this phi. Okay, so we would have taken m1 u1 cos phi over here.
Okay.
Had this u1 been at an angle, we would have taken only the x component of it, because right now we are talking along x-axis only.
Right.
Okay, again, to simplify things, I would just want you to remember this simple statement, that yes, the law of conservation of momentum which we used to do solve our examples with, that is again true, but now we are applying it separately on x-axis and separately on y-axis.
Right. Can you just show me on y-axis so I don't get confused?
Okay, I'll get to the y-axis again, but I want to revert back to the original drawing that I had made, because that would also show. something which I want to show. Okay, this. Okay, now let's talk about along y-axis.
Okay.
Along y-axis. Okay, what is the total momentum along y-axis before collision?
0.
Excellent, excellent. So formula stays the same. M1 V1. Here we I should have written U1x and U2x, and here I will write M1 U1y plus M2 U2y. All right, and now their components after collision is, I mean, M1 V1 stays the same, M2 V2, but now V1 will have to be multiplied with sine
Yeah. Okay.
theta 2, and the second one would have to be multiplied with sine theta 1.
Okay.
That's it. This particular component, it will come out as 0.
Right.
So if I were to write a simplified statement for this law of conservation of momentum, coming back to this diagram, it would be, so for example, I'm talking about two bodies only. uh, so it would become m1 u1 along x-axis plus m2 u2 along x-axis is equal to m1 v1 x plus m2 v2x. The same way for y-axis it would be m1 u1 of y plus m2 u2 of y is equal to m1 v1 of y plus m2 v2 of y. I'm sorry, I was writing on this slide. All right.
Uh-huh.
Okay, I don't think there is this rocket example which they have done in let's say Allahu Akbar, which they have done to in their own particular complicated way of calculation. I don't understand that. I mean, I understand things better this way. You can read that particular example, and if you are fine with their way of calculating it, fine. Otherwise, we will do this calculation in with the way we have learned this formula.
What is the way that they did it? Can you show me?
I've sent you the book. Have you downloaded it? I was about to
Yeah.
assign you reading.
Yeah. I'm on it right now.
Okay, so it's on page 16 and 17 of the PDF. That's what you're about to read right now. Another thing you might ask, where is the actual, let's say, application of this thing? We have got multiple these space bodies which we have had fear that they'd come and collide with the Earth, asteroids. Okay, so
Uh-huh.
actually, we have had missions from NASA uh, whereby they calculated what's the particular velocity of this body approaching the Earth, and if we want to divert its path, at what particular path should we shoot off something which goes on and collides with this thing, and by virtue of its momentum it would change the path of the second body after collision.
Uh-huh.
Okay, so they have I mean, this deep impact mission they have mentioned that it was actually a mission by NASA. I was looking the other day, and time and again there have been calls and there have been deliberation about other asteroids whether they should launch bodies to change their direction of motion or not.
Alright.
uh, this is this um, if you could read all these three examples which are given over here, I mean these three pages, page 16, 17 and 18, and then we can come to the questions. We'll solve them together. The
Okay.
questions mentioned on these 16, 17, 18, we'll solve them together. I just want you to read the rest of the stuff
Okay.
once.
Sir, can you mute your mic? Please. Sir, can you explain the second part of the worked example?
All right, all right, all right, all right, all right. The worked example second part where they're calculating the theta.
Uh, no.
I meant to do this whole worked example together using this formula the way we
The
have done.
first worked example one, the
Worked
first
example
page.
1. Okay, this one.
Yeah.
Okay, they're using that impulse is equal to change in momentum and impulse is equal to force multiplied by time. They're equating the two things to calculate force.
Well, what is the second one you said?
Impulse is equal to change in momentum,
Yeah, what's the second one?
and impulse is equal to force multiplied by time.
Impulse is equal to force multiplied by time. Okay, so the second I just used for. Okay, got it. Okay, okay. Now you can mute again. Thank you. So after after collision for the
Hmm.
figure C and or what's going
Hmm.
on?
Hmm. Hmm. Let's do this example together. Let's do this example together.
Let's just do after collision.
We'll have, okay, after collision, the two things they come combined together and they're moving off at an angle to x-axis. Imagine this thing going along the x-axis, this rocket. Then something comes and hits it from underneath. It would change its angle a bit, and the two are
Right.
now embedded together and they're moving off together.
Right.
So that is what is happening, like the examples that we had where m1 m2 were separate before collision, and after collision the two masses they had, I mean they joined together and they became a joint mass and had joint velocity after collision.
Right. But how come it's P total equals root this square plus that square?
The total momentum after collision, since it's at an angle to x-axis, you can consider it in the form of a right angle triangle.
Uh,
This is happening at an angle and it has a y component, it has an x component. So because of laws
okay.
of momentum you can separately calculate those components, and combining the two you can get the total p, and using any three, two out of three sides of this right angle triangle you can find out the angle. It would take some time to sink in this thing, I mean it's new.
Velocity
Hmm.
after?
Hmm.
What about that?
Velocity after that would be the same for the two bodies, since they are moving off with the same velocity, I mean they have become one body. There would be just one velocity with which they are moving off after collision.
Uh-huh. And how did they come to that formula?
uh which formula? Which
P
one?
total divided by m rocket plus m
Okay,
multiplied.
total momentum divided by momentum of a rocket and momentum of,
Mass of rocket and mass of meteor.
sorry, okay, total velocity is what? Total velocity is the sum of two masses times their, I mean you have total momentum which is equal to m1 plus m2 times v.
Uh-huh.
Total momentum is equal to bracket m1 plus m2 bracket close v.
So we're just making P is equal to mv into
Huh.
V is equal to P by m.
Hmm. Hmm.
Okay. Uh, P total.
I mean, it would be really good if you had a pen and paper with you, and as they, even if you followed their steps, or if you followed the steps that I just taught you, those x and y axis thing, in whatever case, at least once solve this example.
Did they ask me to do this thing? What do you say? What did they want me to do in the end?
In this particular, I mean the requirement of each question is different. We are talking about, somebody could ask you what is the velocity of a particular body after collision, what is velocity of the other body after collision. I mean the masses won't change in collision, so it's just the velocities which are changing. They could ask you to calculate, right now the bodies, they're both moving off in the same direction at same angle, but if they were moving at different angles, they could also have asked you in the question for the angle at which the velocities shoot, or at which the two bodies they go off after the collision.
Right.
So all these things they could be asked in this question.
Okay.
Also read this practical skills thing would come in handy later on when we are having when you are to attempt for that last practical. P6
Yeah.
it is this time.
Okay.
Okay, did you read the exam tip on the right hand side of this book explanation where it says exam hint? Page 17 of PDF.
I will.
Read it. It's just the tip for the exam. For example, when you're solving in the exam and they've given you a particular value and they asked you to recalculate that value. When you recalculate, to show that you have actually done the calculation, give it to one more significant figure than what's given in the question, as a proof that you have actually solved this question.
I may see. Okay, sir. Wait, I have to read 18 also?
Yes, please.
Okay.
It's again another application of having known this concept. Now they're giving you a situation where they had this asteroid, which, I mean, whose course they had to turn about. So for that they've done this, given this calculation, the data and the calculation. So read it. If you want me to help you solve it, we'll solve it together. Otherwise, just read it, read its calculation, and then we'll solve the checkpoint at the end of the chapter together.
I'll just read it.
Hmm.
Sir, so here the asteroid is only moving one direction,
Mm-hmm.
and the impactor is also moving only one direction.
Hmm. I mean, now
But
you have
how
to
does that work?
how you have to now you have to calculate that to change direction by how much you have to give a momentum at what angle. So, for example, previously before launching the this particular projectile, that at what angle do you want it to make impact with the do you want it to make impact with the asteroid?
Yeah, but if you're launching something from Earth and it's not at the same angle, I
I
mean,
mean,
like that you
that
want.
is the thing. We make space objects, human launched space objects move in particular directions. I mean, you do the whole calculation that I'll send it into orbit, it would take this dimension. If I send it into orbit this way, it would take this dimension. That is left for the NASA scientists to do. Ask Mark Zuckerberg about that. But as far as this question is concerned, eventually when it makes the impact, we wanted to make impact with this particular velocity, uh, whereby we'll have the let's say momentum as well of this object, and we have the momentum of the object which is already moving. So at what particular angle we wanted to make impact with that.
Right. Okay. Anyways, I'm done. Let's do checkpoint. Sir. Checkpoint. Hello?
Can you hear me now?
Yeah.
Okay, I'm saying just keep a pen and paper with you because you need one to solve question 2 onwards.
Okay, give me 1 sec. I'll be back.
Hmm.
Hello? And
Hmm.
okay, what is impulse needed to car stop that has a momentum? Impulse is equal to force into time,
Hmm.
right?
Hmm.
And they've given us momentum. Momentum is m into v, right? So I don't need that. So 22,000 is equal to force into time, and yeah, just 22,000, isn't it? Just 22,000.
Hmm. So we'll use the formula over here. If we have to calculate the impulse mv minus mu, final velocity we want to be zero. So final momentum is zero. Initial momentum is 22,000. So impulse
Right.
will be minus 22,000. Minus just shows the in the opposite direction to the initial velocity in which the object was initially moving. What's the unit for impulse?
Um,
Force into time. It's Newton second.
Newton second. Yeah.
Okay, next part, please.
Uh, See, you wrote mv into m this thing, but we're not given the mass. MV.
We don't need the mass.
Yeah, but you wrote the mass.
I wrote MV. So MV at least we know. We don't know M and V separately, but we know the combined MV.
But whatever, okay, just
Hmm.
whatever. If the car brakes could apply force, how long would it take to bring the car to a stop? Car brakes, I think, would be the impulse, right?
Car brakes. Yes, we would be applying the if we are applying force for a particular amount of time. So yes, it's impulse.
Okay. I'm confused.
Shall I open that past paper formula sheet for you?
Oh wait, no, now I know. Uh,
Hmm.
so this thing. Okay. 22,000 divided by 6800. That's the answer.
Hmm. So what we need to do over here is correct. We have got impulse is equal to force into time. We have the impulse which is 22,000. I wrote 2,000 over here. 22,000 and divided by force which is 6,800, and it gives me time in seconds. The time will be in seconds. So it would be 3.24 seconds.
Noise.
Okay, next question please.
In a
Okay,
push,
and next question, just a precaution. It doesn't ask for actual calculations in this one, so you'll just have to give the answer in theoretical form. It doesn't ask for particular calculations. And there is one more thing I'd like to tell you after you have given me answer of this question number two.
uh, in a push shot, the cue ball has mass, travels at 6 meters per second, and it's stationary black. Ball in the middle of the of one end of the table. Black shot also. Black ball also. What mass? Yes. So can you mail?
Hmm.
Okay.
Hmm.
I need to do actual calculations of
No, no need to do actual calculation. Just give. I mean, in simple plain English, if you could explain what would happen to the cue ball.
the cue ball would move at an angle.
What do you think would be that angle?
I think that that angle would be 45.
Hmm. It would be 45 degrees. So, with the velocity that it hits, this one goes off in the upper corner. The cue ball, most likely at 45 degree, it would come down into the lower corner, lower pocket.
Right.
Since it's happening in the middle of the table and they're exactly splitting off at 45 degrees, at a slightly, I mean, had they been slightly, the collision been in the upper half of the table, then the cue ball would have hit the opposite frame, again coming down at 45 degree. But right now at 45 degree, it goes down into this pocket, the lower pocket. Another
Okay.
thing, which I think now could have told earlier as well, but now let's see. Two balls or two bodies, they are colliding along x-axis, and then one moves off in this direction. Let's say v1, and the other moves off in this direction. Let's say v2. Uh, their momentum before collision was how much?
Uh, the same.
It was zero. If I talk about along y-axis,
Okay.
since they were proceeding along x-axis, the momentum along y-axis was zero. Okay, so total momentum before collision along y-axis is zero, and total momentum after collision along y-axis is, call it theta 1, call this theta 2. So it will be m1 v1 sine theta 1. Nothing profound in it, but if you take it one step further, it would give me m1 v1 sine theta 1 is equal to minus m2 v2 sine theta 2. So depending on theta, if the angles are the same, angles at which they split off, the velocity with which the velocities, they are almost mirror of each other. There could be a case, as in this case, in this particular collision, the minus sign only denotes the velocity in opposite direction. This would have y component in this direction, this one would have y component in this direction. Not always the case, but in some cases we get this. Obviously it depends on v1 v2 and theta.
But it's not the same here, no?
mm, Over there,
But over here, what about like over here? I mean, like textbook.
it travels away at 45 degree and 4.24.
Yeah, and the
Okay,
white
so
one short
so
is six.
let's see.
Just the
So
mass is same.
0.17, it would go off with a velocity 4.24, and it is sine 45. Sine 45 is what? Whatever. Okay. The other one also has a mass. This would be equal to
0.17
0.17. Okay.
into 6.
V sine theta we don't know. Are we given the
6. Ah, no, we're not given V. U is 6.
V2 is not given.
Yeah.
U2 is not given. So if I simplify it, it would become like this. Uh, M1 V1 sine theta 1 is equal to M2 V2 sine theta 2. So 0.17 times 4.24 or
Yeah.
0.424. 4.24.
4 point.
That's quite fast, but 4.24 sine theta 2. 0.17 cancels. uh, V2 sine theta 2 is equal to what? 4.24 times sine 45. How much is it? Where is the calculator? Where is the calculator? Oh my, here it is. Here it is. So 4.24 times sine 45. 4.24 times sine 45. This gives me 2.99. Okay. So let's say it is roughly 3, almost equal to. So V2 sine theta is 3. Now it depends at what angle it shoots off. Let's say it shoots off at 45 degree. If it shoots off at 45 degree and I have got 45 degree over here as well, the sine 45 would also cancel out and 4.24 will come equal to V2.
But how do we know this?
Right now we don't. Right now we don't.
Yeah, so
Usually,
how do we
usually,
know?
usually the case is that usually the case is that when they are coming straight off like this, and it's making it go this way, this one would also go in the opposite direction at the same angle. Ek, just one
Okay.
more second. The black ball, 45 degree, ending up in the corner pocket. Hmm. Okay, we can make an assumption over here to solve things. So for example, we can make another assumption that if the collision is elastic, which is the next question. So if the collision is elastic, then velocity is conserved. V1 will be equal to V2. And if
Which one
v
is elastic? Which one is
uh,
inelastic?
in elastic collisions, the kinetic energy or the velocity kinetic energy is conserved. In elastic
Okay.
collision, kinetic energy is conserved. Okay. If
Okay.
kinetic energy is conserved, the velocity it had over there. Anyways, if kinetic energy is uh, v1 will come out equal to v2,
Right.
or v1 sine theta will come out. Here we have got two variables. We have got a variable of v and we have got a variable of theta. So we'll have to make an assumption for one. That is why I told you that in this particular question, the book also doesn't require you to solve uh, exact to calculate the actual value. It's
Uh-huh.
not possible. Either they have to tell that it moves off at the same angle, then you can calculate, or they give you the hint that velocity is 4.24, it goes up with the same velocity, this one goes down.
Uh-huh.
Okay, so we have to make in some cases we I mean, it also depends on the how much spin you give to the ball. This in this particular equation, it does not account for spin, but that could also tell that in which particular direction it would have an impact on the angle at which direction the cue ball goes off in after the collision.
Right.
Okay, so this question, this particular collision, it will be an elastic one because kinetic energy is conserved. Let's see part. Calculate how fast the impactor c. Figure F3. Figure F. Do they tell by how much we have to alter the course? By 1 degree. Here it changes by how much degrees? 1.7 into 10 raised to the power minus 6. If we were to make this alpha, they're saying that you have to redo this question with alpha is equal to 1 degree. Read question number 3 and tell me if this is what it means.
Okay. Calculate how fast impact is enough. Figure F will have to be traveling if it is to alter degree. Um. Mm, mm, right. So we just have to
Let's
change P
let's
imp, right?
let's draw the diagram. Let's draw the diagram.
No, so we just need to do tan theta. Um, this thing
Do the
just
okay. Do
replace
then do the
1.79 by with 1,
do the
and then
calculation and let me know what's your answer.
I don't have calculator. This is too much of
You can you,
complication.
you can use the sine calculator, tan calculator on internet as well. It's easily available. Open a tab,
Okay.
write trigonometric calculator.
Okay.
Found one?
No.
Let me find one and send you the link. Hmm, this one. Here, chat. Control V. Sent in chat.
Okay. Okay. What's this? I don't know how this works.
Slide down. You'll come down on slide. Control V. You'll come down to the portion where it gives you the calculator sign or whatever you want to calculate and put in the value. What you want to do? Sine inverse, right?
Uh-huh.
Does it give you in this one? What's arc sine? Arc sine is sine inverse? Yes, arc sine is sine inverse. Let me try arc sine 1.
Just by
Calculate
just
90 degree. Yes, arc sine is or arc tan you'll have to do.
adjacent adjacent by hypotenuse. Okay, I want to do can you just put in your calculator
It's
or
on the screen.
what
I'll
I
put
tell
it.
you?
Sure.
I just put cos inverse
Cos inverse. Okay.
uh 7.69 into 10 raised to the power 14
Into where is into? Okay. Into 10 raised to the power 14. 14 or minus 14?
14 divided by 1, which is that itself.
This is cos inverse, right?
Right.
It's giving me an error. Let me try one more time. Cos inverse 7.69 into 10 raised to the power 14, you said.
Yes.
Method.
Hmm. What do I have to do?
You have to calculate the velocity of the impactor if we want to change the trajectory of the steroid by 1 degree.
Yes. So what is 1.79 into 10 raised to the power 6?
1.79 into 10 raised to the power 6, that is 1.79 into 10 raised to the power 6.
Minus 6, minus 6.
I mean, that is the answer. You want me to do cos inverse of that?
How many degrees is that, like in number form?
Oh, 10 raised it would be point 0.000500179,
So I just have to
almost
increase the
zero.
speed. Yeah, so I just have to increase the speed of uh this thing, the impactor, to make it 1. So
See,
how would I do
wait, let's see. Okay, so uh, this is the path of, let's see. This is the way asteroid is proceeding, and this is the path of impactor white.
that? See, we
But
just have to increase this thing, right? Impactor speed. That's all I have to do.
hmm, but by how much?
Yeah. So
So it says that we have to make an angle of 1 degree over here.
is there no way we can replace that answer that we got, 7 point something raised
Okay,
by
wait,
minus
let's see,
6,
let's see,
with
let's see,
1?
let's see.
That's what I was trying to do, but I couldn't.
Hmm. Okay, so this will be the final momentum, P final. Okay, this is
Yes.
P asteroid, and this is P impactor. So
Yeah.
asteroid is already moving with a velocity. How much? Horizontal velocity is, comet's mass is 7.23. So this is 7.23 into 10 raised to the power, how much? 10 raised to the power 13. That's the mass of this thing. Okay.
Right.
Uh, the velocity of this thing is how much? Is it already given?
Mm-hmm.
No, which one do we have to alter? F
Impactor.
Apophis. Which one is the mass of Apophis? There are a few masses given over here. Uh, the mass of this one is 6.1 into 10 raised to the power 10. So 6.1 into 10 raised to the power 10. 6.1 into 10 raised to the power 10. They have given us stories of two, one which they have altered and one for which there is a proposal. There have been some calls for a mission to crash a spacecraft into Apophis
Yeah, I
in
read
order to
that.
move it out of crash line. This one is 6.1 traveling at 12.6 kilometers per second. So multiply by 12.6 into 1000 divided by 3600, which make it divided by 3.6. So this is the momentum of this particular thing. this asteroid.
Uh-huh.
Okay,
What is it?
6.1 into 10 raised to the power 10 multiplied by 12.6 by 3.6 would be 12.6 divided by, no, I did it wrong. 1000, it would be 0. 12.6 multiplied by 1000 divided by, oh wait, I did it right. Yes, divided by 3.6 is right. Okay, so this is the velocity of asteroid.
What is it?
12.6 divided by 3.6 is 3.5 meters per second. The velocity over here in the question, it's given in the form of kilometers per hour, converted into the form of meters per second.
Kilometers per second is given.
Meters per second. It's kilometers per second. Allahu Akbar. No, 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 no. 12.6
So,
kilometers per second. So I simply have
yeah,
to multiply it with 1000, 12,600. My bad. My bad. So 12,600 I multiply with. Okay, now I've got it in meters per second.
okay. So 12,600.
Hmm. So the whole this thing becomes 6.1 into 10 raised to the power 10, 6.1 into 10 raised to the power 10 multiplied by 12,600. It becomes 7.686 into 10 raised to the power 14. 7.686 into
Into 10 raised to power
10
14.
raised to the
Okay.
power 14. Okay. Uh, the velocity of impactor we have to calculate. What's the mass?
Uh,
4000 kg.
4,000. Yeah. Sir, if you go down,
Hmm.
just go down. You see right there, like that angle, the angles that are drawn is for the figure G.
Okay.
That is for the question that we've been asked.
Okay.
So the theta there is the answer given down below, lower
Theta
down.
over here is, okay.
That is the answer. So what we need to do is just change the I mean P of impactor to make sure that theta becomes 1, right?
P of the impactor so that theta becomes 1. Hmm.
Yeah. So, isn't there a way where we can just write theta is equal to 1 and then P of impactor is question mark
Hmm.
and then find out P of impactor?
Wait. Wait. If I am given, okay. Okay. So this is horizontal. Okay. So I am given in this right angle triangle I am given theta, and I am given theta and I am given adjacent.
Yeah,
Okay, and I want to put it in calculation in which along with adjacent, all right, opposite. So tan theta is equal to opposite over adjacent.
right.
Okay, so tan 1, I was about to come to this thing, but okay, tan 1 you'll see why we need the calculation we were doing. Tan 1 is equal to what's opposite. This was the opposite calculation that I was about to complete. It has a mass of 4000 multiplied by an unknown velocity divided by the momentum of this thing, 7.86 into 10 raised to the power 14. Got it?
Its screen is frozen. 1 second.
Can you see now?
Uh, yeah, I can see it.
I'll refresh it anyways.
I see it. I see it.
Okay, so 7.86. So now rearranging things, I get uh, V is equal to divided by 4000. Okay,
Uh-huh.
so this gives me 10 1 times 7.8 into 10 raised to the power 14. 7.86 it is. 7.686. Did I copy it right? 7.686? Yes, 7.68. 7.68. 7.68. It's not 7.8, it's 7.686. Okay. 7.686 into 10 raised to the power 14 divided by 4000. So I get answer 3.3 into 10 raised to the power 9 meters per second.
Yeah, so that's the answer.
Do you see what's the problem with this thing, with this answer?
Um, no.
It's greater than the speed of light.
Oh, so?
So you can't move it with an impactor of this particular velocity. You'll have to use an impactor with
Don't
uh
we have planes that move faster than the speed of light?
no, we don't.
What is that sound?
The travel supersonic planes we have got, nothing travels faster than the speed of light.
Pathetic. Okay.
Yes, yes. Opposite over adjacent. Opposite is 4000. Is the mass of this thing given as 4000? This thing with which we have to hit. Hmm.
When were supersonic planes invented?
Not sure. Concords,
Recently?
Concords were supersonic, yes.
Like in the 2000s?
First, no, I think before that, supersonic plane. Oh, 1973.
We managed to crack sound so long ago. We can't crack light.
I mean, even before that, because this is commercial. The first supersonic passenger carrying plane was built in 1973. So the first plane for war purposes or whatever,
Hmm.
it was even before that. Hmm.
Does it damage people? Like,
It damages the plane itself. They crash if they hit into the sound barrier.
uh,
So if
and
they're traveling exactly at the speed of sound, they'll crash. They have
so
to
how?
travel slightly faster or slightly lower.
Uh,
Ideally, a lot lower or slightly faster. Because slightly lower would again keep building that sound in front of you.
mm-hmm.
When you're traveling faster than the speed of sound, you'll always be ahead of sound.
So crazy. I want.
Okay, okay, this done. Fourth, fourth. Shall we do
What?
fourth as well?
Um.
For the experiment shown in figure D,
Yes.
suggest two improvements that could be made to improve. Okay, which particular figure is it talking about? More
B.
observable in the video stills. Hmm. What do you suggest?
And I don't even understand the experiment.
Okay, we'll start from this experiment in the next class. I'll explain it first and then we'll talk about its improvements. Alright?
Okay, sure, whatever.
Okay,
Sir, but
okay. Let's
can you
do
send me
this
that
this
email?
way. Let's do this way. In the